the ratio that dates change. So metamorphic rocks, by their very nature, are not reliable rocks to date. Can't use them. Sedimentary rocks that are made of fragments of older rocks that's been broken up, transported, reaccumulated, re-cemented, made into new rock. Can we use those? No, why not? What are we dating when we date a sedimentary rock?
A bunch of different rocks.
Yeah, we're dating a bunch of different rocks, aren't we? We're dating all those different pieces of different rock that came together to make that sedimentary rock. So we're kind of getting an average of all those original age dates. Not very meaningful, is it? So with sedimentary rocks, we don't date those either. And that's a lot of the rock column. So that's kind of saying the thing that we're going to use, we're going to specifically have a closed system, we're going to know that we started with nothing but parent, and that we aren't skewing and resetting the dates. That means we're pretty much stuck with looking at igneous rocks. Rocks that came from a melt, that started right there at the beginning. Now, they can start today down in Kilauea as that lava pours out of the ground and hardens into basalt into rock. That'll work, we can date that. But it's got to start with those constraints of closed system, known parent, no daughter, and that it's not had its clock reset. So that means that if I have a pile of rocks and I want to date everything, the only thing I can date in there and get a good, honest date is an igneous rock. All the other stuff is undateable. But we have relative age dating where we can put things in order. I'll show you how that kind of gets around some. That's where we need to think in terms of our cross-cutting relationship ideas. Okay, so those are kind of some of the constraints that we work under when we're trying to get good age dates. Now the other thing that we consider and we work hard at is this idea that we're doing it accurately and we did it correctly. So whenever we take a sample of an igneous rock, we'll often take 3 or 4 samples, and not just in the same exact spot, but we'll kind of take them from different parts of the formation. And we'll break those samples into various pieces, and we'll send a piece of each of those samples to 3 or 4 different labs that are doing the age dating work. This way we know there's not something peculiar or unique about that one sample location. And by having different labs run the dates on the different samples, we can compare and contrast them. And that way, if for some reason one lab sends us a date on a sample that just doesn't make any sense compared to what the other 3 labs said, well, there's our red flag. The immediate thing is, something's wrong with what that lab did, or there's something wrong with that sample, and we'll trace it out and we'll get the problem fixed. Or if we can't figure out what's going on, we'll simply eliminate that sample and we won't count it. So science needs to prove the dates, and we need to do everything we can to accurately ensure that we're getting good dates that make sense and follow rules. So when we hear people say, oh, well, how do you know that those age dates, those radiometric dates are correct? Well, science has gone to a lot of effort to ensure that and has cross-checked it, double-checked it, and made sure that they're getting the right answers, not just making it up or just accepting the first answer that pops up. So if I go back to our cross-section that we've looked at in the Grand Canyon, what can I age date here? Out of this whole section, all of this is still flat-lying sedimentary rock, isn't it? This is tilted sedimentary rock. I can't date any of that. The only thing I can date is this Zoroaster granite. That's igneous rock. Now, I can try and get dates out of this Visnu schist, but that's a metamorphic rock. So I'm going to be real suspicious of any dates I get from Visnu schist. But I might try to date a couple of Visnu schist samples right next to the Zoroaster granite. Because when that granite was a hot magma and intruded into that schist, it metamorphosed that schist, baked it right along the edge of that hot magma intrusion. So I look at the date of the Zoroaster granite, which I know is good because that's an igneous rock. And I look at the date of the metamorphism in the Visnu schist right along there, and I can kind of go, it ought to be about the same. Even though it's been metamorphosed, I know from my date on the granite, when that magma intrusion came in, I know when that metamorphism should have occurred. And that should have reset the clock on the Visnu schist right at that point. And if it matches up, then I can kind of go, okay, that's giving me kind of a reference point. I can maybe get a little further away and see what the reference point is there. And it should be older. So it gives me a way of kind of pushing it a little bit, but realizing that that's what's going on. But the granite, I can get a good date. Now, we've got dates between Zoroaster granite and nearby Visnu schist that comes in right about 1.8 billion years. Getting down to pretty old stuff. So everything else from this nonconformity on up has to be younger, right? Now, we've looked at these rocks in other places, and in other places, they've got some lava flows in between them, and we can date those. So that's giving us some constraints on when the sedimentary rocks have to be deposited. And knowing the ages on some of the fossils in here, now we're able to put some ages to these rocks, even though we can't date them. We can get them in a relative, we've got them in a relative order, but now we can start putting some ages. And we know all of this is Precambrian down here, so that's greater than 560 million years. This being 1.8 billion. That's a big unconformity right there. And we know we've got rocks that now range from Cambrian, Devonian, unconformity here, so we're missing some section. Then we've got the Carboniferous in the form of the Mississippian and Pennsylvanian, and the Permian, and there's the big Permian unconformity at the top of the section. So we can start kind of getting some dates, even if they're not spot on. We can get them at least kind of in the bracket. And if I have a couple of lava flows, for instance, here I've got one I can date at 400,000 years. Here I've got one I can date at 200,000 years. Well, this sedimentary limestone in between, I can say, well, its age is no older than 400,000 and no younger than 200,000. So it gives me a way of at least bracketing that sedimentary package. And as I carry that sedimentary package around by looking at the fossils and identifying the unit based on the fossils, I now have a way of taking the absolute age dates I figured out off of these lava flows, and I can carry that around with the sedimentary package to areas where I don't have the lava flows. Which is kind of interesting sometimes. Okay, so this is kind of a way that you don't just use the absolute age date, but you use it along with the relative age dating techniques that you've already learned. And you can really extend these absolute age dates a lot further than you think. So here we've got a situation where we've got a volcanic ash bed here that we can date at 160 million years, And we've got a dike that's an intrusion up here that cuts through, dated at 66 million years. So right away, I know Morrison Formation is older than 160 million, and I know this overlying unit is younger. And this dike cuts in, but this was the surface at the time that dike was in place. It doesn't cut the Wasatch Formation. So that's telling me the Wasatch Formation has to be younger than 66 million years. So I've got a couple of instances where I've got some good solid absolute dates, and I can use my cross-cutting relationships now, my relative age dating techniques, to carry that and at least bracket some of the things that I can't do. Remember we saw this picture before when we were talking about key marker beds? Well, when I look at it, here's the dikey bed, the ash bed here. Here is the Milbrig up here. And these are ash beds. This is volcanic ash. It's igneous. It's good solid dates. And both of these dates come in, and I can follow them around the basins, and they come in here. The dikey is very early Ordovician, and the Milbrig comes in right about here, somewhere in about the middle of the Ordovician. So I've got these marker beds with absolute age dates that I can carry for all of the eastern United States and even over into Europe, and I know the ages, and I can put them together. So clicker time. True or false? Sedimentary rocks are ideal candidates for radiometric dating. I'm going to give you 15 seconds. Okay. Did everybody get it right? You want to bet everybody got it right? Oh, a couple of you weren't paying attention. Okay. Yeah, sedimentary rocks, they just kind of give us this average of all their different components. That really doesn't tell us anything. So sedimentary rocks, we don't even bother with trying to date. They just don't give us solid dates that we can trust. Okay, just a real quick mention of a few other types of age dating that we can use. They're not very common in the sense that we don't oftentimes find samples that we can use these techniques on, but they are available. They're pretty cool. One is called vision track dating. Here's a mineral. You can see all these little lines through it, and what's happened is as isotope decay has occurred, these little high energy electrons have been zipping through this mineral, and as it did, it actually kicked a few of the atoms out of their spot in the atomic structure, kind of pushed them aside as this electron zipped through, and that left a little track, and you can actually see that track in the mineral. And by looking at these tracks, and it's a rather complicated process, we won't go into it, but we can actually date when that occurred. So this, if you can find a sample that shows vision track evidence, we can actually get absolute age dates off of that. So that's kind of cool. One that you hear a lot about, you may have done it as a class project back in high school, and that's Tendo Chronology. And that's just a big fancy way of saying tree rings. Count the tree rings. And tree rings are very unique for the trees. A wide tree ring indicates, hey, it was a good year, a lot of growth. A narrow tree ring says, tough year, maybe it was a drought. Even fires that scar the tree can leave a very particular type of mark. So every tree basically shows its growing seasons in the different pattern of tree rings that develop. And these can then be used to look at other trees or other pieces of timber. For instance, here we have the ruins of an old cabin. We can look at the timbers that were used in the roof, and in this case, Well, they've got these particular green and blue bands that are unique in here. They're not colored like that, but we're just coloring them to show that they're unique bands. And they go to this dead tree and show that that dead tree was pretty young when these were occurring in this timber, when it was a tree, when it was pretty old. And we can use that thing, and now it says these older bands here match the younger bands in this tree that's alive. So we can kind of see a few generations of tree growth and look at these unique tree patterns, these ring patterns, and hook them together to see where these old timbers came from. But you'll notice that doesn't get us back very far, does it? We're talking maybe hundreds, a couple of thousand years maybe. That's not very far geologically, is it? So this is a great technique if you're doing archaeology and you're looking at trying to reconstruct ages of habitation at sites where you might have some old timbers or some wood from an old fire that didn't get burned, and see if you can't maybe hook the rings together with other things in the area. But geologically, this isn't going to help you much. I mean, geologists think in terms of hundreds of thousands to millions of years as being young. This doesn't really do much for us. Another one that you hear a lot about is carbon-14 dating. And again, this is a great archaeological tool, not so much a geologic tool, although for the last couple of ice ages it's not too bad. Basically, again, it's this idea of isotopic decay. In this case, we have the nitrogen-14 isotope. It captures a helium and becomes carbon-14. And carbon then gets absorbed by living tissue. So plants, trees, animals, us, we absorb carbon-14 isotopes. But when we die, we stop absorbing these carbon-14 isotopes. That's it. And what happens is those carbon-14 isotopes start to decay by beta decay, which we talked about, going back to nitrogen-14. So here we are with our parent material in the living organism decaying to daughter material in the organism. This process we can date back to about 75,000 years with any accuracy. After that, we can go to 135,000, but the accuracy just kind of falls off, and we really don't like those dates a lot. So it's great if it's within 75,000 years. A lot better than doing dendrochronology with tree rings, but still in a geologic sense, that's pretty young. Where we do dendrochronology and where we do carbon-14 is when we look at, say, glacial deposits, and we find a tree stump or something. We find a tree that was buried by the glacial ice that then dumped sands and gravels and buried the remains of this tree. That's great if it's the last ice age, the last, what we call the Wisconsin ice sheet. That started about 75,000 years ago and left here about 9,000 years ago. So for Wisconsin age glaciation, carbon-14 and in the very end stages, dendrochronology, do work if we can find organic material from these glaciers that, the organic material was buried and incorporated. That's pretty rare. You don't see that very often. Although there is a spruce forest that was buried by the glaciers that sits out in the bottom of Lake Michigan today that we've been able to date, and we know exactly when that forest was overrun by the glaciers. That's kind of cool. So when we do get something, it's usually pretty spectacular. But all in all, dendrochronology, carbon-14 technology is primarily an architecture or archaeological tool. One of the things that we do with glacial retreat, oftentimes all this meltwater has no place to go. All the channels are still blocked by ice, and these big giant lakes form right along the edges of glacier, what we call a proglacial lake. And they